Very good evening to one and all. I think I'm visible to you. Just a minute. Okay. So, very good evening to one and all. Thank you for your presence in our 30-day masterclass on advanced VLSI design and verification. So, can anyone respond in chat box? Is my voice is clear? Uh, can anyone respond in chat box? Is my voice is clear? So thank you for your joining. Very good evening, Bharatraj Singh. Thank you for your daily presence. So Vaishnavi PV, Sampath, very good evening. Venkat, very good evening. And then Pranav, very good evening. Narayana Murthy, very good evening. Clear, sir. Thank you, Narayana Murthy, for your valuable response. So let's wait for a few minutes. So then we will start at the sharp 7:05. So today we are gonna see FIFO memory, FIFO buffer, FIFO synchronizer. So today our topic is clock domain tracing. So it's like I will tell you one by one what is a clock domain tracing. So how the FIFO are used to make a synchronization between the two clock domains. So let's wait for a few minutes and then we will start the session. So yesterday we seen RAM, RAM code, RAM outputs. Today we are gonna see FIFO. So basically both RAM and FIFO memories are similar. So but FIFO usage is different between the RAM. Okay, RAM only for storing the data's purpose. We can read and write from the RAM. So we can read from particular data and then we can write to particular data in the RAM. So same thing, but you can't choose the memory location in the FIFO memory. So why? Because of you can write only from top and then you can read from the bottom of like a from last memory location of your FIFO memory. Push front, pop back kind of thing. So I hope you guys are familiar with the FIFO working. So FIFO memory, FIFO buffer, first in, first out. So whoever with start with the process means you will get the result at first. So it's like a queue. So the first person will get the access very firstly. So last person will get the access or anything very lastly. So this is a main thing of FIFO memory. So FIFO is very important as a VLSI design engineer. So why? Because of we are dealing with work. We are working with clock frequencies. We are working with multiple clock domains. So in the chip, if you take in like a single chip, there are a lot of clock domains. Okay. So Sri Satya, very good evening. So let's wait for a few minutes. So yesterday we seen RAM and then last class we seen test bench architecture for UART. So you can also take an example of UART with different baud rate devices. So today we are gonna see FIFO memory, FIFO purpose, FIFO architecture. So and then FIFO working, FIFO synchronizer by using the two flip-flop. So and then we'll see the basic information about FIFO and then we'll execute code. We'll execute one code of FIFO. So Joyce Saudri, very good evening. Better Thoughts, very good evening. Thank you for your presence here. So I think we can start now. So FIFO is one kind of memory and also it is kind of buffer also. We can use as memory buffer and then we can use as a synchronizer. So synchronizer. So basically what is synchronizer means. So for example, if you take any chip like any SoC, for example, if you take in like a Snapdragon 800 series SoC, it's kind of chip. Chip means system on chip. It having the CPU cores, it having the GPU cores inside a single chip, and then direct memory access. It having the modem, it having the peripherals, it having the display unit, it having the audio processing unit, it having the analog to digital converter. So and then it having lot of blocks, like a lot of blocks inside the single chip. Okay, each and every blocks are work with the different clock pulses. Why? Because different clock domains. For example, our CPU core will work at 2.5 gigahertz. GPU core will work at 3.5 gigahertz. So the main we having the only one clock input. If assume like a we having the uh, clock input for one SoC. SoC is 800 series, Snapdragon 800 series SoC. It having the clock input of 4.2 gigahertz. This is a 4.2 gigahertz of input clock frequency for that particular chip. Okay, so inside the chip it having a lot of blocks. So we seen the SoC architecture and computer architecture in the previous sessions. So it inside that it having the lot of blocks like the DMA controller, and then modem, and then MIPI protocol, and then net memory access. So and then where it having RAM, and then it having the cache memory. So and then it having them, so it having some general purpose IO pins, and then it having analog to digital converter, audio process, video process, and then graphics unit. So it having a lot of blocks inside the single chip. Okay, each and every blocks are works with different clock frequency. Assume for example, CPU with its work based on the 3.2 gigahertz of frequency, and then CPU core will work based on the 2.5 gigahertz of clock frequency. So direct memory access will work based on the 1 gigahertz of clock frequency, and then ADC will work based on the 500 megahertz of clock frequency. So it's like this. It will work different clock domains. So if all the domains, all the blocks, like I will show you the picture, then only you can easily understand. SoC architecture. So you can refer the SoC architecture. Okay, so just a minute. So this is the one SoC architecture we having. So it having the 4 processor, so like a 4 CPU cores. This is one first core, this is my second core, this is my third core, this is my fourth core, and then this is my memory, this is my bus, basically like a AMBA protocol AXA bus. So it having the audio block here, Bluetooth block here, Ethernet block here, I2C, SPI, UART, universal C series USB port here, so USB block here, timer, analog digital converter. This is an example architecture of one SoC. So it having a lot of blocks, like each and every one is kind of block. So core block, Ethernet block, audio block, Bluetooth block. So each and every block works based on the different clock domains, clock frequencies. So CPU cores, all these 4 CPU cores are works based on the it's example only 3.2 gigahertz of clock. Okay, and then inside the each core it having the cache memory. So if you read the architecture of the SoC architecture of SoC or any CPU core, means each and every CPU core it having the L1 cache memory. L1, there are variety of cache memories, L1, L2, L3 cache memory. So the difference between the cache memory is speed and then how far from the CPU core. So L1 cache memory are near to CPU core. So inside the every CPU core, this is my CPU core 1. Inside that I am having one L1 cache memory. So the cache memory works based on the different clock. That's the CPU core is working based on the different clock. Assume like a core using the 3.2 gigahertz of clock, and then like cache memory works based on the 2.8 gigahertz of clock. So both are different clock domains. So you can't make synchronization between them. Why? Because of one device will send the data very fastly and the receiver device will receive the data very slowly. So you can't make synchronization. If you make communication between without synchronization means you will get the unknown values, you will get the bugs, you will get the errors. So you will receive the unaccepted outputs. So for that you have to synchronize between them. So how you can make synchronization means you can use the FIFO. Okay, you can use a FIFO buffer, you can use a FIFO synchronizer. So this is a basic example of FIFO asynchronous FIFO buffer. So assume like a system A, system B. So system A is working based on a different clock frequency. It is 3.2 gigahertz. It is using the 3.2 gigahertz of clock pulses. And then system B using the 2.5 gigahertz of clock. So it is very slow, it is very fast. So if you directly make the communication, means definitely you will get the errors. You can't make the communication between them. Why? Because of they both are not synchronizing. So if you want to make synchronized, means you can use the asynchronous FIFO. So there are two kind of circuits: synchronous circuits, asynchronous circuits. So we already seen this difference between the synchronous, asynchronous in our previous classes. So synchronous is nothing but using the same clock domain for all the devices. So asynchronous means it is depends on previous there is no different, there is no same clock input for the all device. This is the difference between the synchronous, asynchronous, asynchronous. So there is no dependence of same clock in the asynchronous FIFO. Okay, so this is asynchronous FIFO. So how it is work means, so this is like a buffer. So yesterday also I written one diagram, so I will show you again. So thank you for JK, thank you for your presence, Radhika, Better Thoughts, Kesavan, JK, Tarun, Vasu. So thank you for your presence. So I will write on, I will open my paint. So this is my system A, this is my system B. So inside here I'm having the FIFO buffer, so and then so this system A will write from the top of the FIFO buffer. Okay, and then from this system B will receive the data from backside of the FIFO buffer, like a last index of the FIFO buffer. So it means it will the system A will write the data very fastly inside the FIFO by incrementing the index of the FIFO buffer. So it having some memory locations like this. So by using the pointer or address, we can increment the memory locations like a 0, 1, 2, 3, 4. We can increment by using the right pointer, read pointer. So I will tell you the architecture in upcoming slides. The main thing is, so it will write firstly here in the first index, it will write the first data, then it will write the second data here. First data will come over to this, and then it will increment one by memory locations. So and then it will reach here. From it, if it is reaches here, means the receiver device will get the data from this FIFO buffer. So and then it will send to the receiver system. So the main thing is we are making the communication very good. So this is the main usage of FIFO buffer. Okay, this is a basic example of FIFO buffer. You can assume like any devices. You want different bauded devices, different clock domain devices. It having the 3.2 gigahertz of clock. It having the 2.5 gigahertz of clock. 2.5. Okay, so both are different only. So this is how the FIFO we are working, and then there are a lot of techniques in clock domain crashing. So the main definition of clock domain crashing is, so there are a lot of different clock domain blocks here in our chip. So we need to make synchronization. We can use any techniques like a FIFO technique, and then pulse synchronizer, and then there are a lot of synchronizer techniques we have. So you can use anything. The basic simple and the basic synchronizer is FIFO buffer synchronizer only. By using FIFO, you can make synchronization. Okay, so this is the architecture of the FIFO buffer. So assume like this is my FIFO buffer. So if you want to write into memory, means you need you need inputs of data is a first primary input, clock and then reset is also primary input, and then address is very important input. Why? Because of based on the address only you can read from the memory, and also you can write into memory. So without address you can't do anything here in the FIFO. So same thing. So here we having the data in write underscore en. It means write enable. If it is high means the FIFO you can write into FIFO buffer, and then if write enable is low means you can read from the FIFO buffer. So and then W clock is clock. I say it's this W clock for right clock. So right clock, why I am declaring W clock means it's a right clock. So this is a signal from the this W clock are using this system like this system A clock frequency. Okay, so and then R clock is nothing but this system clock frequency. Okay, so and then data out and then read enable. So these are the basic input and outputs of FIFO buffer according to this synchronization. So according to this circuit or logic. So and then in the FIFO there are a lot of control signals like a FIFO full, FIFO empty, FIFO overflow. So how we can assign like how we can say FIFO is empty, so how we can say FIFO is full. So if the address pointer is starting of this like a first location means, so you can say that the address is pointing the first location. It means FIFO is empty, so you can write into FIFO. Okay, if the address pointer are pointing the last location of the FIFO buffer means, it means already these already remaining memory locations are returned. So the FIFO right pointer is pointing the last memory location. So we can say that FIFO is full, so you can't write more data. So when you can write data means once the FIFO is empty means you can write into FIFO. Okay, this is how it works. So and then for that reason I'm having the separate module right pointer handle, read pointer handle. So this right pointer handle will do the work of giving the address pointer for write operations. Okay, so this read pointer handler will do the work of by using this and read pointer handler only we can read from the data. So we can use anything. So the main difference is here main thing is here we can read and write in simultaneously, but so if you read and write means you will get some unknown values. So without so how you can say means, so we know that setup time, hold time, metastability state. So the signal must be stable in setup time and also hold time. So while writing into memory and then reading from the memory in the single clock cycle, from the one passage, if you are reading from memory and also you are writing from the memory, so you are writing into memory. So it means in the single passage you are doing reading operation and also you are doing the writing operation. It means you will get the unknown values only. Why? Because of you are getting unknown values means, so a signal must be stable up to one clock cycle only, then only you will get the correct value. So in the first clock pulse you can write into FIFO. From the next clock pulse only you can read. So if you are reading and writing the same clock cycle in the same passage of clock means, so the system won't understand. Why? Because of you are reading and writing at the same time. So there is no stabilization in the circuit in the clock. So you can only do you can write in from first you can write to the memory from by using the first clock cycle like a first passage, and then second passage only you can read from the FIFO buffer or FIFO memory. So this means you need the two flip-flops. It's like a two flip-flop synchronizer. So I will show you that circuit. So this is very important. Why? Because of you can to get the metastability to get the result without metastability or without error, without unknown values means you can use these kind of techniques. It means two flip-flop synchronizer. I will show you the circuit in upcoming slides. I think it's clear for you. I hope you are getting my point of FIFO buffer. So and then it's time for if you guys are really interested in this 30-day masterclass, you can convert into 1 month of internship with benefits of all 30 days recording session, all the 30 days of PPT you can download, and then you will get the exclusive 4+ projects. So with regarding the FIFO and then protocols of UART and then AMBA, AICTE, APP protocols, and then you will get the IETE confirmation letter, and then you will get the 180 days of LMS access. It's like a literally 6 months of access. You will get the recorded sessions. You can access for 6 months. So and then you will get the assignment and task we are providing weekly, and then you will get the internship report. Okay, and then finally you will get the IETE internship certificate. Okay, at the end of the 1 month of internship. These are the benefits you will get at the discounted fee of just 999. Our regular fee is 499, but in this masterclass period you will get the this offer. This is limited time period offer. You will get this internship program by using this link. So if you click on this link, means you will see this window. Here you have to choose in the domain site, you have to choose advanced VLSI design and verification. So if you click this registration link for internship program, you will see this window. You have to choose here advanced VLSI design and verification. So and then after the completing 1 month of internship, you will get this certificate from IETE. So this is sample certificate. Okay, so this is the process of getting internship from pantechelearning. So and then this is I am telling. So coming to the content, so this is what I am telling. 2 flip-flop synchronizer. Why? Because of you are in the single clock cycle, you are doing 2 operations from the for the in the single clock pulse, like a single passage. So if you doing like that, means there is no stabilization is in the process. So you will get definitely you will get the metastability state. You will go to the metastability. Metastability means unknown values. You will receive the x0, 1, anything you will receive. Okay, so to neglect that, to remove that, you can use 2 flip-flop synchronizer. You can see here in the first clock cycle it will get the data, it will store for 1 clock cycle. So in the next clock cycle only this second D flip-flop will get the result from this this flip-flop. Okay, so it means, so there is a safety, like here we are using 2 clock cycles. So okay, here this is for first clock cycle, for second clock cycle. So we are using 2 clock cycle, so we can say that our data will be in this safe state. Safely we can read the data from the signal by using this kind of register, by using this kind of techniques, 2 flip-flop synchronizer. So by in this circuit level we can use 2 flip-flop. While writing the code, you have to use 2 registers, 2 temporary register you can use for this kind of technique. So here I am saying like a 2 flip-flop synchronizer. So how you can implement in Verilog or SystemVerilog code, means you have to use 2 register. So for example, I want to assign A equal 5. Okay, so this is my main, so A is my main signal, A equal 5, but I can use another but I am using another signal like a B, like a temporary signal, temp. So I'm having the 2 signals, A and temp. So firstly I am assigning A signal into my temp, and then temp, and then I'm assigning temp equal to B. So I will write once. So firstly so I'm having the signals like a reg output. This is my signal. Okay, this is my output signal. So how you can use as double synchronization, means you have to use double register. So firstly I'm using one temp here. So this is my data in. So I'm using the another register. This is my, the temp is my internal register. So this reg output is my port list output signal. Temp is my internal register, so internal signal. Okay, temp. So firstly this is my input signal, D in my input. So D in reg D in. this is my input, the D in my input. I want to assign the input D into output signal. So output is my output signal. So I want to assign D into output. So if you directly assign means you will get a metastability state while you are doing the same passage means you will get the metastability state. So by you can use the temporary register. So how you can use means firstly I am assigning to my temp and then output equal to temp. So by using this logic, firstly I am assigning the value from D into temp and then temp to output signal. If you follow this means this is a process of two flip-flop synchronizer. Okay, so I hope it's clear for you. So and then I will move into, this is a circuit of two flip-flop synchronizer. It is very important. Okay, so same thing, say whatever you see in this diagram, it's the same thing. So you can see here I'm using the two flip-flop synchronizer. Why? Because of, so while dealing with the pointer, whether you can use binary address or gray code address, binary coded address or gray coded address. So what is the difference between the binary code and the gray code address means? So if you use the gray code address means there is a difference between only one bit of previous one and then current coded data. Why? Because of the binary with having the one or more bit difference. So binary coder means nothing but, so binary code is nothing but okay, binary code. So like assume like a 00 00 and then 001 and then 0010. So this is a binary code. This is like a binary sequence. So I'm going to, if you are using this continuous sequence of binary address means you will get this kind of errors, metastability error, and then you will get the unknown values. So if you use the binary gray coded, so gray code means gray coded sequence. So like a 001 and then 0 0 0 sorry sir 0 0 1 0 0 0 1. So if you compare this means, if you compare like here, just a minute. So if you compare this both binary sequence means there is only one bit difference. Here also there is only one bit difference. This is a gray coded binary code, so the gray coded results. So it will differ by only one bits of sequence. So if you follow the gray code method means you will do the operation very exactly. Gray coded binary inputs, like a you have to convert the binary code, like you have to convert this binary sequence into gray code, and then you have to use that converted gray coded for the address purpose, address pointing. Okay, if you use like that means you can neglect that these kind of errors, metastability errors. Okay, so that's why I'm using the gray. You can see here G refers to gray coded right pointer, read pointer. Here also read pointer, right pointer. Okay, this is how it works. So by using the pointer we can read from the buffer and we can write from the buffer, but here there are two clock domains. One for this clock domain for given this clock domain is given by system A, then this R clock domain, read clock domain, is given by system B. Okay, so system A will give the one clock domain for read or write, and then system B will give the one clock domain for this buffer to read and write. Okay, so this is how it works. So system A will give the clock domain for system A will give the will give the right pointer, like I will give the pointer for write. System B will give the clock domain for read pointer from the before buffer. Okay, so this is the main thing. The main thing is system will give the clock in domain for write into FIFO. So system B will give the clock domain for read from the FIFO buffer. So it will do write, it will do read. System A will do the write, system B will do the read operation. Both are different, both are using different clock domains. Okay, so the asynchronous before will make the communication between these system A, system B very smoothly. So I will show you the code. So you can see here. So same like I'm showing the design like system A, system B, write pointer, read pointer. So I've written the code based on this circuit. So based on this block diagram, FIFO buffer, write pointer, read pointer, same like I'm having the clock domains. So same I'm having the modules. This is my design code module. This is my top module, asynchronous FIFO. So here I am doing instantiation of 5 modules. My first module is synchronizer for my write pointer. This synchronizer is for my read pointer. You can see here read pointer, write pointer, and then this is my write pointer handler. So this I'm instantiating with the read pointer handler, and then I'm instantiation of FIFO memory. So firstly I will show you the FIFO memory. So FIFO memory is nothing but it's like a FIFO memory is nothing but we are creating some memory locations. So and we are telling in how many bits you can store into FIFO memory in one memory. So how you can create means yesterday also we seen the how to create the RAM. So this is a memory creation. Memory creation. Okay, the input signals of write clock, write enable. So W is refers to this signal is given by this clock is given by system A. So system A will do the write operation into FIFO memory. Okay, so write is refers to system A clock, system A signal. So write signal, write clock, write underscore en, r clock, r underscore en. So and then I'm having the parameter. I'm having the parameters of binary. So firstly I'm having the pointers like addresser. Pointer means it's telling the address of memory location. It will pointing the memory location. So firstly I am creating the pointer in the binary method, in the binary only by using the binary sequence, binary pointer. I'm creating the binary and then I'm converting into the gray. Okay, but I'm actually going to what I'm going to use means I'm actually going to use gray coded pointer only I'm going to use. So first for that reason I'm creating the binary pointer. So for read and so write handler also need one pointer, read handler also need one pointer. So I'm creating the 2 pointers here. So this is for write pointer, read pointer, both are binary. Then data in, so this is my input data, and then I'm telling the FIFO full and empty condition. So and then data out, this is my data out from the FIFO memory. So this is my data empty, data full and empty condition, like a memory full and empty condition. If so write by, you can see here binary b underscore write ptr. This signal is referring as binary write pointer. Okay, so if it is if write enable is high and then FIFO not in full state means I'm doing. So you can see here write enable is high and then FIFO not full. So full, it is I'm using here logical not symbol. You can see here that exclamation symbol is referring to logical not. So logical not of FIFO full, it means FIFO is in empty state. So you can write into data. So I'm writing into the D. You can see here I'm assigning the D, whatever my data input I'm assigning into my FIFO memory based on the write pointer. Okay, based on the write pointer. This is my memory creation, data with underscore -1 down to 0. It means data with having the parameter of 8. So 7 down to 0 and then depth is 8. So it means we totally having the 8 memory locations. each and every memory location I can store 8 bit of data. This is a memory. So it's like a 8 memory location. Each memory location I can store 8 bit of data. It is a small buffer, small FIFO buffer. So based on the pointer I am writing into my FIFO buffer. So I am directly assigning my D in data to my right pointer. Okay. And then D out. So D out means based on the read pointer I have to assign the data from FIFO buffer to D out signal. So D out signal is going to give output for system B. So based on the read pointer, you can see here B underscore RPTR. It means binary underscore read pointer. So based on the read pointer, I'm accessing that memory. I'm accessing that memory location. So I'm assigning to my D out data. So this is how basic FIFO buffer is I created. And then so I'm using here read pointer, write pointer. Okay, so how you can increment the read pointer and decrement read pointer? So firstly I want to write from first location, second location, third location. So I have to continuously increment my write pointer, then only I can write to my all the memory location. Okay, so I want to increment. And same also in the read operation also I want to increment from the first, second, third, fourth, fifth up to 7. So I want to increment my read pointer, write pointer also. For that I am using the two module like a read pointer handler and then write pointer handler. Okay. this is that module. Same signals we have in the read clock. So this is given by the system A, R clock, R reset, R underscore en. So and then here I'm doing the gray code operation. Okay, so gray coded pointer synchronization. So this is my binary read pointer, gray code read pointer. So these are my signals like output empty signal. So so write pointer means it will do only writing into FIFO buffer, FIFO memory. It will do only writing. Okay, so how it will do means it will increments the one by one my memory location. So if it is reaches the last memory location, I can say that my FIFO memory is full, so you can't write no more data. So for that reason I am using some output signal. So by using this signal you can say the output of empty, so empty or full condition. So this is the logic of this. So you can say here you can see here I am converting the gray coded to binary coded to gray code output. So you guys are may aware of the converting binary to gray code. Okay, binary to gray code, it is nothing but so we need to XOR of the current and the previous bit. So I will show you that diagram also. Converting binary to gray code, binary to so this is a binary to gray code conversion. So this is my binary input. So firstly you have to directly take this bit, directly come over here, and then you have to do XOR operation of current bit and then previous bit. So one XOR of 0 is 1. So and then same like you have to do like this. So this is a formula, this is a logic I am doing in my code. So you can see here I'm doing the right shift. Right shift means it will do right shifting. It will do one bit shift of right, so I can access that particular bit. So I'm doing here, you can see here this symbol is referring as XOR symbol. So I'm doing XOR operation of current bit and then previous bit. This is the conversion of binary to gray coded. So you can see here gray code pointer next. So and then I'm finally assigning my binary pointer next to binary main signal, and then gray pointer next to my gray pointer signal. So if you sit and see this code means you can easily understand. I'm just assigning from LHS to RHS. So LHS is sender, RHS is receiver, the kind of thing. So and then if reset is not I means empty is 1. If reset is reset is like having 1, it means So 1 means 0, so if it is having 1 means it will do RMT, will give the RMT value. So this is how it works. So and then same like here I'm doing the right pointer, and also I'm having the read pointer also. So read pointer, so it's like a read pointer. So for right pointer, so same like we having the right pointer also. Right pointer, this is my read pointer, and then another thing is synchronizer. So synchronizer is nothing but I am using the 2D flip-flop for my synchronization. This is a circuit for that. So inputs are clock, reset, D in and then D out. But here inside my here I am using one internal signal for my synchronization purpose, 2 flip-flop synchronizer. So firstly I am assigning the D into Q1 and then Q1 to D out. So this is my Q1 is my internal signal, temporary signal. And first I am assigning the D in the direct first input to my temporary signal to my output signal. So if this is a method of doing the 2 flip-flop synchronizer. Okay, this is a method of doing the 2 flip-flop synchronizer. So this is a design code. So in the top module of asynchronous before, I am including all the files, all the design code files. By using the tick include, you can include that particular files inside your current code. Okay. So and then this is my main input and output signal, write clock, read clock, write reset, read reset, write enable, read enable, data in, data out, full and empty. So I'm using some internal signals I'm using some wires here. So I'm instantiating all the modules in my top module of asynchronous before. So and then I will return some test benches. This is my test bench. Here I'm instantiating the my top module of design code with test bench here. So you can see here this is my top module of design code. This is my test bench. This is my top module of design code. So this is my test bench internal signals. This is my parameter. This is my clock creation of. So you can see here the main thing is you can see here right clock. This is a kind of creation of this clock this clock are given by system A. The frequency is 10 nanosecond of off time. It means 50 megahertz. 50 megahertz. Okay. So and then this clock is given by system B. So the clock frequency is, so I need to convert nanosecond is to 35 ns to megahertz. So 35 megahertz to mega. So to totally 28.357. So 28.57. So 28.57 of megahertz. So system A clock is 50 megahertz. System B clock is 20. sorry. So we need to take 70. So why? Because of 10 nanosecond off time, 10 nanosecond on time. So totally 35 plus 35 70. So sorry for that, 70 nanosecond. So toggling means from one clock cycle off time is low, off time is high. So we have from that only I can do toggling. So if you do toggling of clock cycle with 10 nanosecond means 10 nanosecond is on time, and another 10 nanosecond is on time. So on time and off time, 10 for off time, 10 nanosecond for off time, and then next 10 nanosecond for on time. So both on and off, combination of on and off clock is one clock cycle. So the total time taken of the one clock cycle is 20 nanosecond. So for 50 megahertz, the time taken of one clock cycle is 20 nanoseconds. So I know that, but I don't know for the 70 nanosecond. So 70 nanosecond approximately 14.28. So 14 point, I can say like a 14 megahertz. So the system A clock frequency is 50 megahertz, system B clock frequency is 14 megahertz. So I'm created the two clock domains. One is 50 megahertz of clock, another one is 14 megahertz of clock. So it means 10 nanosecond off time, 10 nanosecond on time. Here 35 nanosecond off time, 35 nanosecond on time. So it will toggle from this only. Okay. So it means both are different clock domains. So it will, the system A is very working very fastly, system B is very low speed. So this is my clock creation. This is the, from for that reason only I am written the FIFO buffer. Okay. So and then here I am giving the stimulus for my signals, clock 0, right clock 0, right angle 0, data in also 0, and then after that I'm just on my reset condition, off my reset condition. Then again I will do this repeat loop. Here I am writing some data with u random. So you can see here u random means it will assign random data, random input for my input signal. So and you can see here pushback. So pushback is nothing but so pushback, it means I'm putting off data from the to the FIFO buffer. Okay. So and then here in the initial begin, I am doing the read operation. So you can see here read clock, read reset, read enable, and then I'm just off my reset condition. Here I am reading from the memory locations. Okay. So and then this is for displaying the waveform output. So I'm just writing into my FIFO buffer with random values, and then I'm reading from the FIFO buffer. Okay. So this is a display statement for to check my output, to check my result. If data out is not equal to W data, so W data is nothing but write data, data out is nothing but output of FIFO buffer, output of system B. If both are matching means our code is working correctly, so we are getting correct output. If both are not matching means system will giving the wrong output. Okay. So it means there is some issue in my design code. So based on this is like a self-check test bench. So comparison of input and output, this is known as self-check test bench. Okay. So and then I will show you the output for this. So I can use the media playground here. So here this is my forking directory. So I'm going to use CostaSim. So for that I just close my CostaSim. I will show you how to run that, then only you can understand. So okay, this is my VS Code. This is my working directory. So inside my working directory I'm having the all the files like a FIFO memory, FIFO handler, synchronizer file, and then write pointer file, design file. I'm having all the file, and also I'm having the run.to file. So in the run.to file is very important for running the CostaSim, using CostaSim. Why? Because of in the Verilog you need to give the all the file names. You have what you are using for the simulation. So you have to give the all the file names. So in the vsim, after the vsim we have to give the test bench name, so test bench module name, and then this is for adding the waveforms, this is for run the simulation. This is a commands for tool while we are written in the run.to file. Okay. So and then in the terminal, you just write vsim. So it will open the tool inside your working directory, inside your current folder. Okay. So I'm just opening my CostaSim. Okay. Yeah, I'm opening to my CostaSim. You can see here we having the files synchronizer, test bench, and then design file. So and then I have to type do run.do, so it will do it will do execution, it will start the simulation. So it will take some time. Okay, so and then you can see here, you can see my output of transcript. So you can see here, I can zoom here. So my write data is A4, my R data is A4, so both are matching, so both are same. So I can say that my design code is working fine. So comparison passed. So and then here you can see here my written write data is a 9e, it's a hexadecimal 9e. My read data is also 9e, so I'm getting the correct output from my design code. So we can say that my design code is working fine correctly. So in the Costa sim you can see a lot of information. So in the view you can click on your view. In the view you can, if you want to see waveform means just tick here, you have to tick here wave, and then transcript structure, and then schematic. You can also see the schematic here, and also you can see the process, you can see the memory list. So memory list means we are creating on memory, we are creating on memory inside my code, we are creating that only. So we are getting some memories like a 8 memory location, we can store 8 bit of data, it kind of memory only. So you can also see the memory inside your tool, the Costa sim. So for that, here you have to click in the memory list. So you can see here memory list, it will open the window. So just click on here, and then it will show you that two memories. So this is my memory, this is my FIFO memory first, this is my first FIFO memory, and then this is my second FIFO memory. So depth is 2, width is 8. So depth is 8, width also 8. It means 8 memory location, width is 8 bits. So this is, so if you create the memory by using the array inside your code means you can see the memory list inside your Costa sim software, Costa sim tool. Okay, this is how you can check the memory creation. So you can see here FIFO memory. So depth is 8, also width is 8. It means I am created the memory location of 8 memory location. Each memory location I can store 8 bit of data. So this is how you can write. You can see also here write data is 99, read data is also 99. So and then write data is also read data also It means I am getting the correct value output what I am written into FIFO buffer. So it means both different clock domains of system A and system B are working fine. There is no data corruption, data error while doing the data transferring between two clock domains of systems. Okay, this is how the FIFO synchronizer is working for different clock domains. So this is only simple circuit, simple design only. While entering into the big topic, big SOCs, chip level SOC means the FIFO size is very it's different. FIFO working also very different. So there are a lot of handshaking signals is there in the FIFO. So overloading, FIFO overloading, FIFO non-overloading. So there are a lot of control signals while entering into different lot of clock domains, and then big FIFO buffer. So this is how it works, and then this is how we can check the FIFO buffer with the two clock domains. So and then this is for today, and then I will show you the waveform window. So I think you can't see the waveform window clearly. Why? Because of there is a small in size. So if you having this tool like a Costa sim means you can see the waveform window here, and also you can use the Xilinx window, Xilinx tool or Verilog tool. You can use anything. If you want to see the waveform means you can use any tool, Xilinx, Vivado, Intel Cortex Prime. You can use this tool. So you can see here my main output signal is data, write data, read data. So this is my data out. You can see here data out signal and then write data. write data. So there is in here write data signal, but I'm finding too late. So this is how it works. Okay, so if you have any doubt means you can ask. No, if I think this is for today. So it is very important important topic, FIFO synchronizer. So the main thing is this. So both are different clock domains. System A having different clock domains, system B having different clock domains. To make synchronization, we are using FIFO buffer, FIFO synchronizer. Okay, asynchronous FIFO synchronizer. So this is a topic today for today. I hope it's clear for you. So and then if you have any doubt means you can ask now. So then if you guys are really interested in this masterclass, you can convert into 1 month of internship by using this link, and then you will get this benefits of these all 8 benefits. It's just a discounted fee of just 999. So and then you will get the recorded sessions, downloadable codes, downloadable PPTs, so and then and more topics. So thank you guys, thank you for listening. If you have any doubt means you can ask now. Regarding the main thing is making synchronization between two clock domains. This is the main thing of main usage of FIFO buffer. So again you can just there are a lot of techniques are making two synchronization in the different clock domains. There are a lot of techniques, so each and every techniques are very important. So it is, if you are trying to get into a VLSI field, you want to work with a VLSI job means, so these are the main interview questions. So there are two different devices. One is clock A, B. So both are working the different clock frequency. So one is sending fast, another one is receiving slowly. So how you can make synchronization? So this kind of questions the interviewer will ask to you. So on the time you can ask, you can reply, you can say like this: by using the asynchronous FIFO, you can make the synchronization between the two different clock domain systems. So thank you for your response, Bharat Singh. So thank you guys, thank you for listening. So we'll see the different topic tomorrow. We'll see the tomorrow. Okay, thank you guys, thank you for listening. Good night.